Okay, today we are going to learn about the optimization using CST. Before we learn about that, we study the basic of antenna. Okay, imagine a dipole antenna. Okay, which of the length of lambda over 2. Okay, then we have another dipole antenna, which is also the length of lambda over 2. In CST, we can put a discrete port here. Okay, so have you ever think that why this particular dipole antenna doesn't have ground connection? Actually, like any other circuits, like in electronic circuits, if we have power, we have some resistor, we should have some ground. So where is the ground of this dipole antenna? So actually, in wave we have peak here and peak here, which is equivalent to lambda. So this peak, let's say we choose this as the peak and this is as the minimum. So this one can be taken as the high voltage, and then this one we can regard is like a grounding, the lower potential. Okay, it's become the ground of the antenna. Voltage, let's say, and this is let's say this, so this is lambda. So in a conventional patch antenna with inset feed, we have a patch antenna, then we have a substrate of permittivity R. Okay, where is the grounding of the antenna? This is the ground. And when we excite a waveguide in CST, it need to have certain dimension. Okay, so the lower one is H and the upper one is 4H. And then we have the width of the waveguide. Let's say width of feet is WF. So the width of the waveguide should be at least 5 times WF. And it can extend up to 10 WF. So it is advisable to model the connector of the antenna so that your result will be more comparable to the fabricated result, to the measured results. Which means if you have coaxial model or SMA connector, you better using them rather than using the waveguide port. So the next part, we are going to study about the optimization using CST. Normally, let's say we have a normal antenna. Let's say we have a very simple antenna with the radiator. Okay, with the radiator here lambda over 2. Okay, now why we only have this dipole of lambda over 2? Because we have a grounding connection here. Okay, have a grounding connection here, so it is enough that this lambda over 2 will operate as the radiator antenna. So when we assign in CST, we need to assign in terms of parametric. Okay, this is, let's say you put it LF, and this is WF, and this is let's say for the width of the substrate WS, and let's say this is the length of the let's say this is the length of the substrate. Okay, if we use this in terms of parametric, then we can optimize the CST using CST on particular dimension to achieve certain target. So before I proceed with the optimization using CST, let me brief some of the very basic formula. So let's say we have S11. Okay, S11 can be in terms of linear, and it can be in terms of dB, which is S11 is actually the signal coming through from port 1 and going out to port 1 again. Port 1 2 means that you have signal coming in and you have signal coming out from port 1. So that's why it's called return loss. So in antenna is in terms of dB scale. Okay, let's say in dB. So we have actually 20 log of S11 in linear. Okay, so let's say S11 linear of 0.3 is actually equivalent to negative 10 dB. The smaller value of, if you have in terms of linear, if you have the linear number is decreased to 0.3, 0.2 and below, then in terms of dB, let's say you can have negative 10 dB or up to the smaller like negative 50 dB, let's say. So this is very important characteristic that we're going to be used in CST setting in order for us to optimize. Okay, let's say later we will optimize the feed length so that this dipole antenna will resonate at our desired frequency. Okay, we will proceed later to the optimization setting in CST.